I wanted to start saying thank you to BRE Trust, to Deborah, and to Peter for this opportunity. And also, this opportunity wouldn't be possible without Joe Clark, who put me in contact with BRE, and I'm thank you to him as well. And also, thank you to the BRE Scotland team. Here I see Rufus and Rory. They welcomed me and they made me feel very good and comfortable, supporting me in anything I needed. And back to my research, life cycle assessment of buildings, focusing on domestic buildings. I'll start saying why did I choose to research this, my motivations and my goals. First of all, when I started my first step on research in Seville, the research group was interested in social housing buildings, which is quite a very important thing in Spain. And I started to get interested on that as well. I saw that there was a very low link between the actual life cycle assessment of those buildings and the reality. And with all the life cycle assessment tools available by then, it was very difficult to compare them because they've got different criteria and different indicators. So it was very difficult to see which life cycle assessment score was the correct one or the best one. Also because social housing developments, which we have been talking about a little bit before me, they are used to be linked to the low-income families and the most difficult environment socially. So that was a very important thing for me as well, not only the energy demand, CO2 emissions, but also the social and economic factors in them. I'm actually starting my final year, hopefully, of my research. It's divided in 4 different phases, but I'm doing a bit of everyone by now. And the first thing was the literature review. And obviously, talking about life cycle assessment, I had to see and read and study about life cycle assessment tools. So that's what I did. I started doing a massive list of all life cycle assessment tools available and see their primary purpose and how could they be used and applied. So I got a few different ones, also not only energy modeling tools, but also quantitative and qualitative tools or rating tools, and see what they were giving me and the output that they had in order to compare the output within them. I had a few conclusions for this study, more than saying which is the best one. Basically, what I saw is the most complex tool, the more expertise you need, the more time it takes you to get the assessment, and the more difficult it is to input and get real graphic outputs for that. So I decided to do a user-friendly life cycle assessment tool for domestic buildings based on MATLAB. I saw that there was a lack of deep end-of-life analysis and also lack of social or economic factors integrated. Those things are things that we see that now are getting more and more important, and life cycle assessment tool or energy modeling tools are trying to get them into their assessment. Also, life cycle assessment was not used in a very early stage of the building process or the design process of the architectural project. That was a main issue as well, because the later you try to modify something, the more difficult it gets, the more expensive it gets, and the less you reduce, in this case, energy demand or CO2 emissions. So this is the summary of my tool, trying to get involved in environmental, economic, and social factors, trying to develop a building model and to describe that physically, get an environmental database and the quantities of that building and match them to get a result, and trying to get the legal framework from the Kyoto Protocol until the UK Carbon Plan or the European directive that we get just now. You see that the economic data and social data are in dashed lines because it was getting very, very difficult for me in 3 years' time or 2.5 years' time to get all these things together. So by now, economic and social data are out of the scope of my PhD globally. They're somehow integrated, and economic data is closer to get into my PhD at the very final stage. As I said, regarding the environmental methodology that I try to produce here, I get the building model, describe it physically, try to get a life cycle inventory of all materials and quantities using that building, and match them with environmental data. The database I'm using by now is the ICE database and EPDs, basically because that was easier for me to match those things. But the main core of my PhD is the methodology itself and the user-friendly tool with MATLAB, not the database. So in case I get a more accurate database, I can easily adapt that to my PhD. All the phases of the database that I'm going to study on my PhD are the one that you see in black, except for the benefits beyond. That's something that is very difficult to value just now because it's something that will happen in a very, very long time period. So by now what I do is to give roughly a value for those things, but it's very difficult to estimate and to get assumptions for those factors. And the indicators I will be using are embodied energy and carbon, which is megajoules, and kilograms of CO2 emission equivalent. This is a brief comparison of my simplified life cycle assessment tool and 2 other tools widely used. In Revit, we get now the tally thing, but it's very, very United States focused, and they use a different environmental methodology, which is not used here in Europe. And in IES, now they've got the impact tool, but it's a much more complex thing than my user-friendly tool, which ideally will be used at the very, very early design stage of the building. Trying to use it as a decision-making thing rather than I've got my building and I want to know how much energy it demands, how much energy it consumes within the building fabric, and how many kilograms of CO2 emissions it produces during the lifespan. This is the methodology that I use with my simplified tool. Get the general information, life cycle assessment information, the building measurements that can be got from a thermal modeling program like IES or Revit, and then describe all the building elements in a very simplified way, getting a lot of assumptions, and match them with the environmental database, and the MATLAB will do all the calculations. Within that, I'll get the environmental loads and hopefully graphically results and very easy to understand. This slide shows where do I get the information from. So from manufacturing stage, I get the database from EPDs and ICE database. I did my own transport tool using the DIFRA values from the UK government. So by now, my tool only is able to calculate transportation by road. Hopefully, it will be updated to get by train and by plane as well. And all the replacement and operational energy needs. What I saw is the operational energy needs is something that is very well documented just now with IES or other energy modeling programs. So I'm not getting into the thermal modeling, I'm just getting an energy demand benchmark. Or if I do the calculation with IES, I'll get that figure from that for that stage. As well, again, beyond the end of life, I'm using the wastages rates from the BRE publications, but it's something which is very difficult to get assumptions, so it's now out of the scope of my PhD. These are all things that I use with all units and indicators for all calculations. You don't need to read all of that. It's just basically just to justify that I'm using a lot of different databases, a lot of different data inputs, but at the end what I'll get is an indicator by square meter of element. So I can easily then say, okay, I've got the 100 square meters of external wall, so I will know the indicator itself. This is the scope of the simplified tool. As I say, it's general information about the building, what kind of building is, always knowing that it's domestic building what I'm trying to assess, but quite easily adaptable to other kind of buildings in the future after a PhD. How to get the building measurements from a thermal modeling or Revit program, or just inputting them. It's not a very tedious thing, so it's easy to get. And then trying to say what kind of elements and what materials are used in these buildings. This will be matched with the database, and the MATLAB will do all the calculations. This is an example of how to define, for example, an external wall, if it's non-insulated, soundproof insulated, thermal insulated, what kind of insulation, and the thickness of that insulation. The rest of the things, you just say to the tool if you're using concrete block, brick, or what kind of material for the leaves. But you don't need to say anything else. It's a very simplified thing. You finish, you select the finish that you've got internally and externally, and that's it. Within the social, as I say, it's now out of the scope of my PhD because it's a very, very large and huge thing to understand. I tried to input accessibility and adaptability, but then it was very difficult to measure those things. And it was very difficult for me to measure those things within 2 years' time, having the environmental things to do. So I had a look to those things, but it's something that will be part of my future work. And the same with economic things. It's a very important part of the life cycle assessment because you really need to know how much it costs you, how much is going to cost a retrofit thing or a new building. So it's something I really want to get into my PhD, and I think I'll get it, but by now I cannot commit myself to put that information also. The expected outcomes is why this simplified tool it should be used as a decision-making tool at a very early stage. So I don't want to be a rival of different life cycle assessment tools. I just want my tool to be a very friendly, simplified thing to know, okay, if I'm using this material, I know that the tendency of that building will be to have this energy consumption in terms of embodied energy, or I will produce these kilograms of CO2 emissions. And then know what direction to get when getting into deeper project management. It's in line with the European standards 15978. It's a full objective thing, so I don't get any characterization or normalization because I don't want to put more importance in some things than others. So it's a very clear study or assessment. And by now it's only for domestic buildings, but hopefully it will be adaptable to any other kind of buildings. And no expertise is needed. It's a very time effective. I just finished the tool or the draft of the tool, and a life cycle assessment could be done in less than 10 minutes. So it's quite a time effective thing. And graphically and easy to understand results is a very important thing, because we all here know some things about embodied energy, embodied carbon, CO2 emissions, or megajoules, but people who are the users of the buildings, they don't know anything about that. So there should be a clear interaction and a very, very good interaction and communication thing between the experts of the construction sector and the users, the final users. This is just the screenshot of the very early draft of my MATLAB tool. It's just to say that it has general part of building information. Then you've got the raw database, which is how to put the building measurements and life cycle assessment data. Then you define all the building elements with all materials, but in a very simplified way. The only things that the user can select is the thickness of insulation, what kind of insulation and what type of finish. And then it does all the calculations and it produces the results. For my case study, I'm using this 4-in-block building, which is in Ravenscraig Innovation Park near Glasgow. This is one of the most typically domestic buildings I would say, in the UK. It says 265,000 in Scotland, and in England more than 3 million dwelling like that. This is a 30s or 70s design, so it's something that now it would need to be retrofit or demolished and new build in a lot of cases. So it was worth to study this case as a domestic building, because it's a very good example for the UK. In this particular case, in the Innovation Park, it has 3 different external walls, because it was done to study different possibilities within different environments. So one half of that building is externally insulated, and the other half is internally insulated, depending on if the user is living in that building, so you cannot do anything inside, or the building is not being used, so you can modify things internally. With these things, I produced a lot of cases. So the 3 ones that I'm going to show here are what I call the baseline, which is the building itself without any modification, so it has no insulation at all. Modifying only the external wall and insulating that externally, and the other case study is improving all the external wall, but also the internal walls. Here you can see a summary of what kind of external wall, partition, and internal walls it has, floors and roof, and some results from all the stages. I'll go into the detail later on with more numbers, but basically we can see here the embodied energy is nearly 4 million megajoules. Okay. And the embodied carbon is 450,000 kilograms. These are the results for the first modification, which is only putting insulation in the external wall and externally. It's mineral wool, what is done, and all the figures are higher, but by stages are roughly the same. And these are the results from the third case, which is insulating internally and externally. Again, figures of embodied energy and carbon are higher, obviously, but the percentages are roughly the same of all stages. Here is just to show, because in that study, as I said before, the use operational energy demand is not included. So getting the good practice from the CIPC Guide F, we can see that in the second and third scenario, the energy consumption could be 87 or 85% of the complete life cycle assessment, which indicates that my tool is giving reasonable results. So I could go deeper in these results to see more in detail those numbers, but it's getting reasonable values. Here we can see different scenarios by building elements, just to highlight that the external walls and the roof are getting the higher number. So in the scenario 3, which is more likely to be a real home just now, we can see that the energy consumption for the building fabric itself of the external wall and the roof is almost 50% of all embodied energy in the complete life cycle assessment. So it's getting me figures and values to see where do I need to put more attention in. And these are the same results, but instead of by building elements, by life cycle assessment stages. So again, it's a lot of numbers, but it's just to highlight that around 50% of embodied energy is due to the fabric. So if we go to the very bottom, scenario 3, the bottom cell of the red one, that means that the embodied energy within the operational energy needs of the life cycle assessment of that building, 50% of that is related to building fabric. And we say that external walls and roof are 50% responsible of the 50% of that, so means that external wall and roof are responsible for 7.5% of the complete energy demand of the building, which is a very large thing to see. And I know that I need to put more attention in those things or play with those materials in order to see which is the best option. These are very early results, so I haven't gone very deeply in this because it's something that I got very a few weeks ago. But it's just to know all the possibilities that this simplified tool could give us in order when you're starting a domestic project. Yeah. So very roughly, briefly. I've said all the possibilities. So as a summary, you can have this slide. Basically, summarizes all the life cycle assessment process and all the process that I passed through all these 2.5 years of PhD just now. That's it. Thank you very much.